Hello, my name is Luzier. I'm the controls lead here at Gatorloop. And today I'm presenting a workshop on sensors and actuators. So first of all, what's a sensor? Well, basically it measures something around it in the environment and converts that measurement to an electrical signal. This may be anything with temperature, acceleration, distance, the color of what it's looking at, or force, or plenty of other things. Now, most of the measurements will be an analog signal, which the sensor converts to a digital signal. So what's the difference? Well, something's analog if it continuously variable. Think of how between 0 and 1, there's an infinite number of numbers. You can just get infinitely more precise. So an analog signal might be like a sine wave, which varies continuously. A digital signal, on the other hand, is composed of 1s and 0s, so there's a finite number of values that can hold. Here's an example. So you have an analog signal. It's kind of going all over the place, it's smooth. Whereas a digital signal, it's just 1s or 0s, on or off. That's it. Now, there's limitations to digital. You can't encompass every possible value. It's just not possible. Usually you'll have a minimum and maximum value that you can hold in a certain number of bits, and also have a precision limitation. So maybe you're measuring acceleration, and you can't get any more precise than 0.1 meters per second squared, something like that. Now you have to consider this because if let's say your accelerometer only goes up to 10 Gs, and you're using it in a up to 12 G application, it's not going to work. You're going to have some problems. So we need to choose the right sensor. So first step, just figure out what you want to achieve. And now there may be multiple ways to do what you want to do. For example, if you're trying to figure out if an object passes a sensor, you might use something that tells distance, and when suddenly distance is shorter, there's something in the way. Or maybe you'll use a color sensor, because maybe the thing passing in front of you is a different color. So there's definitely different options in a lot of scenarios. And so then you want to find a sensor that can do what you want, basically. Then once you have like a list of sensors that seem in the right area, you're going to get more specific with the requirements. So you need to make sure that your expected range of values is going to be within the sensor's capabilities. You need to make sure it's going to be precise enough for what you need to do, depending on your application. You may not need to precise things, you may need something very precise. And you also need to keep in mind how fast response time you need. So for example, on our pod, we need very fast response time to position and velocity change, so that if we need to suddenly brake, we can do it in time. And don't worry about cost, because you can find the best sensor ever, but you may not be able to afford it. So you have to weigh that too. And so one thing you can do when determining what sensor you want to use is called decision matrix. So basically, you list your options here, your various sensors you're looking at, and you list some criteria that you're going to consider. And you'll weigh them differently. So maybe accuracy, maybe precision is more important to you than, say, I don't know, power efficiency, something like that. So we'll give them different weights, we'll give them scores, multiply scores by the weights, you'll get a total for each of your options, and so whichever one's highest will pick. So for instance, option 3 here is your best option, and so that's the sensor you go with. Now, how do you read the data? Well, sensors have a variety of methods to transmit the data. Some just allow amount of voltage through proportional to their reading. This is kind of an analog way of doing it. And I2C is a common protocol. I'll talk about in a second. And some sensors use a proprietary protocol that you have to download their drivers for. So I2C, that's the main one. So you have two lines. You have the clock line and the data line. And basically the data line is synchronized. And so if you look at this chart here, you've got this clock line that just goes up and down, high and low. And then on every high spot on the clock, the data is either 1 or 0. And so over the course of this, you get a message, and it's built up with a start condition, an address, acknowledge, some data, acknowledge, and stop. And so you do this just back and forth. You say, hey, here's some data, and they give you some data back. You can have multiple sensors, for example, on one line. So the master would be your microcontroller, for example, and the slave would be sensors and stuff like that. So if you want to read data from one of these sensors, you send a request, and then you wait for it to reply. here's an example. Our tiny pod project uses I2C to read data from its inertial measurement unit. And that runs on a Launchpad microcontroller and in Code Composer Studio. If I switch to that here, I put up a little script here that I'll just run a I2C to read acceleration data from our IMU. And you can see here that we get some values. It's a little jumpy, so I can fix that, but you'll see that right now it's sitting still, and so it's reading roughly 0 in each direction. There's a little bit of noise. Now the units here are 1/100ths of a meter per second squared. So this 914 is 9.14 meters per second squared. And so see that we have, so our linear acceleration roughly 0, and then our acceleration due to gravity is in all these different directions because the thing's all like sitting on its side over there. If I like rotate it here, you can see that the velocity of gravitational acceleration, you'll see it changes because it's along a different axis. And if I start actually moving the thing back and forth, you'll see the linear acceleration starts actually doing things, and then it disconnects because I moved it too far. All right. So moving on from sensors, does anyone have any questions about sensors before I move on? You can also ask them at the end. So actuators. Basically, it's the things that do what we want. So that might be some motors, some solenoid switches, basically anything that like moves, and even some things that don't move. But yeah. So choose the right actuator. Basically the same thing as sensors. You find someone if you want, you narrow them down, you use decision matrices, and remember that there can be multiple ways to accomplish something. An example I can think of is one of the old pod designs. They needed an emergency cutoff switch. And instead of using like an electronic switch, it was designed by mechanical engineers. So they used a physical switch and a servo that flipped over and hit the switch physically. And it worked. Not sure if that's the best way to do it though. So using actuators. Every actuator you get will have a specification sheet. It'll tell you how to use it. Sometimes it'll just be you give it power and it works, and then you don't give it power and it doesn't. Just like with sensors, we have various protocols. PWM is one of the common ones. So PWM is pulse width modulation. We'll see what that means in a minute here. And other terms to note are period, which is the time of one wavelength, and the duty cycle is the amount of time that the wave is high. It's usually a percentage, but sometimes it's written as an amount of time. So PWM uses a high-frequency square wave, and the duty cycle controls the average voltage. So here we have basically no wave, 0% duty cycle, and full voltage, 100% duty cycle. At 50%, you see half the time it's at 5 volts, and half the time it drops down to 0. So the average is 2.5 volts. And then if you lower your duty cycle more, you have less time high, more time low, so your average goes lower. This enables you to control various things. For example, motor drivers. Your motor is probably going to use a lot higher voltage than your microcontroller can handle. For example, the actuator I have up here is using 12 volts. It can actually handle, no, it's 12 volts. The motor driver can handle more than 12. Okay, so I have 12 volts hooked up. I do not want to run 12 volts through the microcontroller. That's a very bad idea. It will just fry it. And so you need to figure out how to control the energy coming into the motor to control the motor when you can't run it through the microcontroller. And so that's where the motor drivers come in. Basically, you attach your motor here, you attach your battery here, and then over here are some connections for your microcontroller. One of them is the ground, the other receives PWM. So the higher, so 100% duty cycle is full voltage. That will allow the full voltage of the power supply through all 12 volts. 0%, 0%, half, half. So it basically it makes the power going to the motor mimic your PWM. And there's a third pin here that reverses the direction. So let's switch to the example I've prepared here. We've got a linear actuator, a 12-volt battery, Cytron motor driver, and it's being run by our Arduino. So here we go. So it's probably hard to see on the projection here, but I have two LEDs. One is blue and one is yellow. And yeah. So yeah, you can't really see. But the blue one, if you look closely, is getting brighter and then dimmer, and then brighter and then dimmer. And every time the blue LED gets zoomed back off, the yellow LED toggles. So I basically just tie that into the wiring that goes to the driver. So the blue LED is representing our PWM, and the yellow is our reverse. So the brighter the blue LED, the higher our duty cycle is. We're sending more power to the motor. And you'll see when I catch it, it will slowly accelerate and then get fast and slow down, and then reverse direction, get fast and slow down. So we make this here. You know, nah, I got it. I'm just going to wait till the so see it accelerating and then slowing down. So the duty cycle is going down, and now we've flipped the reverse bit, and we start increasing duty cycle again. You see it slowly speeds up, you hear it getting faster, and then it slows back down until it stops again. And I basically just have a loop running, does that back and forth. I'll show you that now. So here we have just a very simple Arduino code. Essentially, I have a boolean for forward that we just toggle. And so to pin 2, we do forward times 255. So 255 is the highest you're at. So the analog signal is PWM. So what I was saying about Actuators is how do we use them together? So basically, basic concept of controls is sometimes things don't do what we want, and we can fix that, usually. So here's some terminology to keep in mind. So the plant is the device we're trying to control, or it could be the actuator or something else. The controller controls the signal that goes to the plant. The system is everything together, the controller, plant, sensor, and there can be multiple all plant together. And the error is the difference between our actual and desired output, where if the output is bigger, then the desired error is considered negative, positive, the other way around. So, closed loop control. The idea is we can use a sensor, and we can see how close we were to our desired output, and we send that back through, and we figure out what to do based on that. So, a really simple controller is called a bang-bang controller. It's on or off. So it's like your air conditioner, right? You set a temperature, and once you get above that a little ways, it turns on, and you start cooling down. And once you get cold enough, it turns off. That's it. There's no like half air AC. It's just on or off. So the next one is proportional control. So it's a little more complicated. Basically, the controller that's receiving an error, it sends an input to the plant that is proportional to your error. So basically, you're saying, oh, are we too low? Let's increase the input. Or too high? Let's decrease the input. And an example of this is like cruise control, like a simple cruise control. Just if you're going too slow, add some more gas. And now, the increase and decrease could be swapped if the dynamics of the system are different, but generally think of it this way. Another example would be, I'll use an example here for this in the coming slides. Imagine that you see some of your friends maybe jogging up in the distance, and you want to catch up to them. Well, the further you are behind, the faster you're going to go. You're like, they're way up there, I got to catch up, right? As you approach, you'll start to slow down. But what happens if we overshoot? Let's say we don't slow down fast enough, and we just run right past them, and then start coming back again. And then we're running towards them, and then they run past us, and we turn around again, and you just keep going back and forth like that. Well, we need to adjust our input as we approach, so we don't overshoot. So we can add a derivative term in addition to our proportional term. So we take the derivative of our error, and if it's decreasing, that means we're getting closer, so we decrease our input a bit so that we don't overshoot. Basically, you're talking to your friends, and you see that you're approaching really fast, and you go, hold on, maybe I should slow down a bit, so I don't go past them. But let's say you slow down too much, and you're not quite reaching your target. Like, you're behind them, you think, hey, I'm pretty close, so you slow on down, but then they're still ahead of you, and you're like, okay, well, let me speed up, and then like it doesn't quite work. So basically, we need to adjust our input a bit more just to get the rest of the way there. Like, we're mostly there. So if we integrate our error, we're basically adding up over time. And if it's big, that means that our error has been there for a while. And so if we want zero error, we want to get the integral down to 0. So if our integral's high, it means we've had error existing for a while, so we need to change something because that error's not going away. So then we'll increase our input, and then we'll catch up. So you're running up to them, because you're far away, you slow down because you start to get closer, but you're still a little ways behind them, so you speed up just a little bit to close that last distance. That's basically what happens here. And so all three together is PID control: proportional, integral, derivative. These three terms can be used in various combinations. You can use just proportional, use proportional integral, you can use proportional derivative, or all three. Basically, what you tend to do is you start with a proportional control, see how that works, and then decide on if you want to use integral, derivative, or both from there. And then you can tweak the values of these terms because they're all weighted with the gain. So your proportional might be like 2, or it might be 4. And so you can tweak these to optimize your response. So maybe you want to get to them, your friends, as fast as possible without overshooting. You'll tweak your response so that you're running up really fast, but then you slow down in the last second. So you can tweak these by like trial and error, or you can do it mathematically. Now, transfer functions, I'm just going to cover like briefly. Essentially, your controller and plant can be represented with functions, and in the Laplace domain, if you're familiar with that. If you're not, I'm not going to explain it, because anyway, in the Laplace domain, they're transfer functions. And in the Laplace domain, you can then multiply these to find an overall transfer function. And the transfer function relates your input to your output, so you can see how the system works. Basically, your overall process for controlling the system is you're going to model the system with a differential equation and try to do a good job. Then you linearize it so that you can do math with it and have it not be just awful to work with. Now, granted, both of these are approximations. So the first one's already approximation because we can't account for everything. Now you're linearizing it, that's another approximation. You just gotta hope it's good enough. So then you perform Laplace transform, and now you have your equation in a transfer function form. You can have poles and zeros, which I'll get to later. Basically, you want to stabilize and achieve the desired response. And then once you have the controller designed, you figure out how to do it. So let me switch over to MATLAB here. All right, so that's a little program here. So let's start with a transfer function. So this is actually from a homework I had last year. So we'll start with this. We have P equals 15 over S squared plus 4S plus 4. Basically, that's derived from a differential equation that represents the system. I believe the system was like an arm going back and forth, and you're trying to, it's for air hockey. So basically, you're trying to block the shots coming in, so you have anything that rotates to block them. Now, what I can do is I can simulate what happens if you give it a response and say, hey, go here. We'll say go to 1, right? So here we go. So if we say go to 1, it's going to do that. Now, not great, pretty wobbly, and you may notice it doesn't actually go to 1. It ends up at like 0.75 roughly. So it doesn't actually even quite make it to where we want, and it like flails all over the place. So first step, let's just try putting in a P controller. So that gives us this. So if we increase the proportional gain, we'll get to 1 faster, but we'll overshoot it a lot. But we also still won't end up at 1, but we'll end up closer to 1 than before. That looks like about like 0.85, something like that. So then, okay. So now my thought is, well, we're overshooting a bunch, so let's add a derivative term. If we had a derivative term of 2, I had a proportional term of 10. If I add a derivative term of 2, we get the following response. There we go. So now, you see, we're still overshooting a little bit, but we're not going like this. So very, much better. so we overshoot a little bit, not that big a deal. The response time is fast. You'll see like, this is 0.1 seconds and we're like there. Now, we're not ending at 1 though, so that's not what we want. We want to end where we want to end. And 0.88, not where we want to be. We want to be at 1. So, let's add an integral term. That should bring us to 1. So, that was the wrong one there. This one. So here we go. I've got an integral term. And you'll see it goes up. It's a weird little sort of dip. That's from the derivative term saying, hey, we're approaching too fast, slow down. And then it slowly comes back up, and you're at, and then you finish at 1, and you get most of the way there pretty quickly, but maybe not quick enough. Like after a second, you're 0.9, so that puck may have just gone past you. So now what we do is we end up like tweaking some values. So my first thought is we need to get there a little quicker. So let's increase the proportional gain a bit. Let's go from 5 to say 10, and we'll see what that does. And so now you can see sort of it's a little faster. It's kind of hard to tell though because it changes the scale above. Let's try increasing that a little more, and see what happens here. So now you can see we get like it goes basically straight up, almost straight up on that side. So we're getting there really fast. But now we're overshooting a bit. So maybe let's fix that overshoot. So let's add a bit more proportional or derivative gain. So then we have a bit more of that. And you see it's just a process. You just tweak it, you see what you're doing. So now we're not overshooting anymore. That's good. But we're not ending at 1, or at least we don't appear to be ending in 1 here. It will eventually go back to 1, but that's not what we want. And you'll see though, due to that increase in proportional gain, we're getting up there very fast, 0.05 seconds. That's pretty good. That might be good enough. You'd obviously have to like test it and see if that ends up being good, but it sounds pretty good to me. But yeah, so we're kind of going away from 1. So we need more integral gain because we're away from it. We need to go back to it. So let's increase that by maybe about the same amount that we increased proportional. Let's see what that looks like. I mean, now you see that's pretty good. Like you tell it, hey, go to 1, and it shoots right up, and then stays right along there. We might even be able to get there just a little bit faster, maybe. Let's try adding just a little more proportional gain. And that's hard to see through the scale, so I would say this is probably pretty good. So we overshoot a little bit, just a tiny bit, but that's not, in this scenario, that's not a big deal. Now, if this was you trying to land a rocket, you don't want to overshoot the ground because then you crash. But for our little hockey puck thing, that's fine. A little bit overshoot, comes back down. So it's pretty much at 1, and you'll see that it gets there very quickly. It's around 0.05. So yeah, so that's basically an example of going through the process. Another method you could do is manually adding holes. I'll show you that. So if I go back to our example function Q, our 15 over s squared plus more x plus 20. So the roots of the numerator are referred to as zeros. And the roots of the denominator roots. Zeros kind of. Basically, if you plug in a numerator, solve for 0, those are the zeros. There's no s's up there though, so we don't have any independent variables, so there's no zeros. But at the bottom, we have some s's, so we have poles. So basically, you plug in s squared plus 4s plus 20 equals 0, solve that. Whatever you end up with are your zeros, or your poles, rather. And basically, those kind of tell you how the system responds. And I can run. That'll take a minute. Essentially, we can bring up this chart that has, and basically you can add poles and zeros manually. So it'll change the equation, and you essentially end up being able to tweak the function to do like exactly what you want by adding these poles and zeros. The only downside is manually adding them is more difficult to implement than a PID controller. So a PID controller, like we just went over it, all you have to do is do like a proportional thing or a derivative of the error or integral of the error. If you're manually adding poles and zeros, you're going to end up with just this crazy controller that you have to somehow figure out how to make. Usually it's just going to be a whole mess of resistors and capacitors, just a big circuit. So here we go. So if we add a, this may not work well because I'm using UFS, so it's trying to run sort of the Wi-Fi. Okay, so this doesn't want to work. Point is, there's another way to do it. Basically, if you look at those charts, you'll end up with like a line, and that'll show you a response to various frequencies. Depending on what class you take, you may know that you could represent any function as a series of sine waves. It's called a Fourier series. And essentially, you'll look at what you expect to happen, and you'll say, okay, I want to get rid of maybe you want to get rid of high frequency inputs, because maybe you have a sensor that's got some noise in it, so it's kind of going like this. You want to get rid of that and only look at the big picture. So you'll end up with like a line, and your like frequency will be here, and your amplitude will be here.